Hello everyone, welcome back to our channel. Dear students, let's discuss the next unit commonly called as infrared spectroscopy. We all know that spectroscopy is a physical technique which is used for the structural determination of chemical compounds. So in this series we are going to have a first technique that is commonly called as what? Infrared spectroscopy. The infrared spectroscopy is also called as what? Rotational vibrational spectroscopy. Why we are calling it as rotational and vibrational spectroscopy? Why? Because if you take any kind of the molecule, in the molecules we are having molecular energies, right? The molecular energies are what? Electronic energies, rotational energies, vibrational energies, right? It means that what? In case of the molecular energy diagram, we are having electronic levels, vibrational levels and rotational levels. So the molecular energies are having what? Electronic levels, vibrational levels and the rotational levels. Suppose if the particle wants to jump from one vibrational level to another vibrational level, particle should cross what? The rotational level. That's why this spectroscopy is commonly called as what? Rotational vibrational spectroscopy. Right? The interaction of IR radiation with the sample brings about the changes in the molecules from the one vibrational level to another vibrational level. During this particular transition, what we are observing, the molecules are going to cross the rotational levels also. That's why the spectroscopy is commonly called as rotational spectroscopy. Because of the combination of the rotational and vibrational transitions, the peak which we are observing in IR spectra is somewhat broader in nature. Okay. See this here. Changes in rotational as well as vibrational levels. This spectroscopic technique is useful for the detection of organic functional groups. Whatever the organic compounds which we are having, in those organic compounds, if you have different kinds of the functional groups, acids, esters, amides, such type of functional groups can be easily identified by IR spectroscopy. Okay. If you take the IR region is divided into three portions: far IR, mid IR and near IR. So what is the range? 1 to 300 centimeter inverse of the frequency. Already we know that the electromagnetic radiation is associated with electromagnetic waves. That's why we are going to have the dual character. Because of the dual character, we are going to have the properties like wavelength, frequency, wave number, etc, 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 right? So if we talk about these kind of characteristic components, indirectly what we are discussing, energy or not. So in the introduction portion we had a clear-cut discussion related to the electromagnetic radiation, the functions of the electromagnetic radiation and the properties of electromagnetic spectrum. Okay, let us see in this case what we are observing. 1 to 300 centimeter inverse, this is the frequency or wave number. So in IR spectroscopy we are using the terminology called as vibrational frequency. Okay, why? Because the changes takes place in the vibrational levels. Because of that reason we are using the component called as what? Vibrational frequency. These are the frequency values. The middle IR region is what? 625 to 4000 centimeter inverse. The near one is what? 4000 to 12,000 centimeter inverse. In order to identify or in order to deduce the information of a particular organic compound, this particular region is very much useful, the mid IR region. So whenever the sample is interacted with the IR radiation, if the IR radiation is having the frequency in between 625 to 4000 centimeter inverse, we are going to get the clear-cut information regarding the functional groups which are present in the different kinds of the chemical compounds. Okay. So what is the source of IR radiation? What is the source? See this one, silicon carbide and oxides of the elements Yt, Eu and Zr, zirconium, europium and ytterbium. These oxides are subjected to heating around 1000 to 1200 degrees centigrade. These are going to give us IR radiations. Okay. So what is the limitation of IR spectroscopy? The limitation is very important. In order to identify the data or in order to identify the particular functional group in a different organic compounds, what should we have? The molecule should have either permanent dipole moment or induced dipole moment. This condition is very much necessary, then only the IR spectrometer predict the information from the unknown sample. What is the condition? The molecule should have either permanent dipole moment or induced dipole moment. See this one, in case of the carbon dioxide, in general conditions we are not going to observe any kind of peak which is related to the carbon monoxide. But if you induce the dipole moment, what should happen? We can observe the peak for the CO2 molecule, right? Already we know that these are the polar in nature, that's why we will observe the permanent dipole moment, and because of the permanent dipole moment we are going to have the information from the infrared spectroscopy. See this one, the IR spectra can be recorded either in solids or in the solution state. So in case of the solid state, what we are having? Potassium bromide pellets. Initially we are preparing the potassium bromide pellets. Those are containing our organic molecule or any kind of the chemical molecule that is subjected to the analysis. We will observe the corresponding peaks in the IR spectra. In case of the solution, we are using a solvent called as nuzol. The nuzol is the what? One hydrocarbon. By using these two things, we are going to interpret the structure of the unknown sample. Okay. We all know that any kind of this spectral technique, the principle is very important component. Right? If you do not understand the principle, you will not understand the further topics which are related to the IR spectroscopy. So let's discuss the classical principle of IR spectroscopy. See this one. Here we are saying that the molecule should have the permanent dipole moment or induced dipole moment. So indirectly what we are observing, we need to have a polar bond. We should have a polar molecule. Here I have taken one polar molecule. Right? We all know that the bond between any two atoms is a spring type. It is not a rigid bond. It means that what? Always the atoms are come close together and also move away from each other. If the atoms are come close together, then the phenomena is commonly called as what? Compression or not. If the atoms are move away from each other, then the thing is called as expansions or not. It means that what? In a particular chemical molecules, we are observing compressions and expansions. So in this particular case, what happens? Because of the compressions, the distance between the atoms are decreasing. Because of the expansions, the distance between the atoms are increasing. It means that what? The position of atoms in the molecules are changing or not. That is commonly called as periodic displacement of atoms from their equilibrium positions, or the periodic displacement of nuclei from their equilibrium position. Then that concept is commonly called as vibration. What is the name? Vibration. Periodic displacement of nuclei from their equilibrium position of group called as vibration. So in the particular molecules, what we are observing? Vibrations. Okay. See this one. The vibrations in the molecule develops what? Electric field. because of the compressions and expansions commonly called as vibrations, what we are observing, electric field in the molecule. That electric field depending upon the what? Nuclear positions. See this one? In case of the compression and in case of expansion, the nucleus positions are changing or not? Once the positions are changing, whatever the electric field is produced here, that strength is going to be changed or not? So because of the change in the strength of the electric field, the produced electric field is commonly called as stationary alternate electric field. That is commonly represented as SAEF. This is present in the form of what? Waves. See this one? In this particular situation, we are observing the compressions and the expansions. Because of the compressions and expansions, what we are observing, electric field. The produced electric field is strength is depending upon the nuclear positions. That's why that is commonly called as stationary alternate electric field. The stationary alternate electric field present in the form of wave. Now what we are doing, this is our unknown sample or not? This is the situation inside the sample. Now what we are doing, we are interacting the sample with the IR radiation. Already we had a discussion related to electromagnetic radiation. Electromagnetic radiation contains two components, electric field and the magnetic field. Both are perpendicular to each other and perpendicular to the direction of the propagation. So what happens, whenever the IR sample is interact with your sample molecule, the electric field component of the IR light or IR radiation is going to interact with the stationary alternate electric field. So we are continuously sending what? IR radiation or not? 1 centimeter inverse, 2 centimeter inverse, 3 centimeter inverse, 4 centimeter inverse. Continuously we are sending. So what is the frequency of your stationary alternate electric field? 1200 centimeter inverse, right? So whenever the IR radiation frequency reaches to the stationary alternate electric field, what will happen? The sample can absorb the IR radiation and produces the corresponding signal. In that way, we will get the IR spectra. After the absorption of IR radiation, little elongation of the bond takes place and a group vibrates with 2 into frequency. It means that what we are observing, after the absorption of the light radiation, the light elongation of the peak, increasing in the height of the peak, takes place. So this is all about your principle of IR spectroscope. Okay, let's continue the remaining portions in the coming videos.